because in some sense they're out of equilibrium in more than one way. Because you're already talking about an amorphous system which is out of equilibrium, and then you're driving it on top of that. Right? So in some sense you have a driven out of equilibrium system. Right? We're back to passive systems here, not active ones, and we're back to theory rather than experiment. I've not made this talk too long, and I realize I'm the last thing between you and lunch. So I don't want to go on too long, but there's plenty of time for you to ask me questions in between if anything's unclear. And what I'll tell you about is work mainly done by Jack Parley and together with Sri Sastry as well. Okay, so here's a nice diagram from a review by Alexandre Nicolas from a few years ago of kind of where you get amorphous solids. And these are really sort of surprisingly common, right? They range in sort of scale from metallic glasses where the particles are basically atomic scale all the way up to granular solids where the particle size goes up to 1 centimeter, okay? And you can classify those along sort of two axes. One is essentially how important thermal motion is, and the other one is the character of the dynamics. And we're going to mainly look at the athermal end, where the particles are big enough that to a first approximation you can neglect thermal excitation. So these are sort of, you could think of granular suspensions, but also foams and emulsions with reasonably big droplets are in that category, where KT is much smaller than, say, the typical surface energy of an emulsion or droplet or a foam bubble. Okay? So that's our setting, and as I've already said, these materials are out of equilibrium. The way they're structured depends on how they're made. These are not equilibrium structures. If you left them for a very, very long time, in principle, most of these things should crystallize, right? So certainly if they're sufficiently monodispersed that the particles are of equal size. Okay? So these are out of equilibrium structures. They're metastable, and they have a history-dependent structure that depends on preparation. Okay, so if we look at mechanically perturbing these systems, one standard protocol is to just make them flow. So you put your material between two plates and you do this, so you do steady shear. Okay, and the result is what's called the flow curve, which tells you how the shear stress that you need to apply relates to the shear rate, so the speed at which you're moving the top plate in essence. Okay? And what you find in a large variety of these amorphous materials is that the flow curve is not what you would get for a Newtonian fluid, so it's not just, the stress is not just a linear function of shear rate, but actually you get something called a yield stress, so you need a non-zero stress to move the top plate even slowly. And then beyond that, the way the stress increases is typically given by a power law in shear rate. Okay? This is called the Herschel-Bulkley law. It's largely phenomenological, so there's not many systems where we have any idea what the fundamental reason for this, although it comes out of one of the models I'll show you later. And this is very common. And sort of there's a nice review of this which has things like chocolate mousse in it, toothpaste, yogurt, etc. Right? Paint also goes in that category. So there's a very large variety of materials that actually macroscopically have this behavior. Okay, so that's very well studied. We're going to look at a different protocol, which is oscillatory strain, which is a similar idea, but you do this with your plate. So you have a frequency and you have an amplitude that you can control. Okay? And what's interesting about that scenario compared to this one is that here all the states that I can explore that are steady states are the ones which are flowing. Okay? Whereas everything that's sort of down here below the yield stress is never in a steady state. Right? Whereas with oscillatory strain, as we will see, there are steady states which are fluidized, so which are flowing, and there are steady states which are essentially elastic, right? So which have not yielded. Okay? And so that's one advantage of this oscillatory protocol. Okay, so here it is. So essentially we have a shear strain which we'll call gamma. We oscillate that in a periodic fashion with some angular frequency omega, and basically you do this to your system, you go backwards and forwards. Okay? Okay. And so what's been known for a few years from simulations, for example, from Ludovic Berthier's group, is that these systems are actually interesting because as you vary the amplitude of your perturbation, right, you get a so-called dynamical transition. So if you look at stroboscopically recorded configuration, so you always go back to the same point of the period, you look at the system and then you compare from period to period, what you see is that above a certain amplitude there is diffusive motion, so there's a non-zero diffusion constant, whereas below a certain amplitude, essentially there's no motion that you can record. So it looks like the diffusion constant there drops to zero, and you have a dynamical transition, not unlike a sort of glass transition at that point. Okay? You can then also look at this in more detail and find the analog of these diffusion results here from the when you record the energy. So what you see there is you have the energy of the system, which you can easily record in a simulation, parametrically plotted throughout your strain cycle. The light gray are the transients, and then the dark lines are the steady state values. Okay? So what you see is that at low strain amplitudes, the energy just goes back and forth, and it's uniquely linked to the state. There's no hysteresis. So that's a system that hasn't yielded, and it's basically just deforming elastically back and forth. The forward cycle is the same as the backward half of the cycle. Okay? Whereas above, you get this sort of hysteretic shape. So on the right here, these right two plots, the point here is a bit, I've got my finger in front of it, that's the problem. Okay? You see here, you basically have hysteresis, so the system is dissipative. Even in steady state, in every cycle, you dissipate energy because you're performing work, as you can work out from the sort of integral inside that closed loop. Okay? So this is another way of visualizing that same transition as here. The states that don't diffuse are basically elastic. The material always comes back to the same configuration, essentially. And the states above that amplitude, they're fluidized. There's dissipation in every cycle. The system is essentially flowing. So what's interesting now is when you combine this aspect, you have this dynamical transition, with the fact that these systems are already out of equilibrium, so how they behave depends on how you've made them, right? They're not equilibrium structures. So there is, in this response that I've just described, there is a further dependence on how non-equilibrium the system is when you start. Okay? And that's in the glass literature typically called the initial annealing dependence, basically how well have you prepared the sample in terms of how low is its energy when you start. If it's low in energy, then you say it's well annealed, as you would do with the glass if you cool it slowly. If it's high, then you say it's poorly annealed. Okay? And so now you can record the steady state energy, this particularly is the inherent structure energy, but that's not important here, as a function of amplitude, and the different curves here are different degrees of annealing as parameterized here by an initial temperature for the protocol by which you make the material. Okay? And so what you see is that the poorly annealed samples, where you've done a bad job of kind of lowering the energy, after you've increased the amplitude, so if you increase the amplitude each time reaching a steady state, they all get to the same point. Okay, so at some characteristic strain, they all seem to have the same state because the energies are all identical. So you sort of strain annealed in some sense these samples. Okay, you've made them better in the sense of lowering energy. Okay, and then beyond that, they all the systems lie on the same curve because everything's been fluidized. The energy goes up again as you increase the strain. Right? So here, as you increase strain amplitude, look at steady states. You see first you sort of strain anneal, you improve. You lower the energy further, and then here the energy goes up again as the system becomes more fluidized. Okay? So that's the poorly annealed samples. It turns out for the well annealed samples, these are even more interesting because here it really depends on how you've prepared the sample, at what amplitude it actually starts to yield. Okay? So a system that's well annealed, you could strain up to a larger amplitude with almost no change in state and energy, until finally at some large amplitude it then becomes fluidized and reaches a fluidized steady state. Okay? So that's this interplay that I said of these two types of being out of equilibrium. You've got kind of the one type of non-equilibrium, the driving on this axis, and the initial non-equilibrium state on the other axis. Right? And it's basically the interaction of these that's very interesting. And then of course, again, one can visualize those using the plots that we saw earlier, where you have these, you record the energy in steady state. Okay. So how can we build a theory of this type of behavior? Obviously you can do particle-based simulations. That's what these results were that I showed you. Okay, if you want something that's slightly simpler, where you can even hope maybe to make some progress analytically, right, you need to identify what's really going on when the material's flowing, so when it's fluidized. Okay, and we know very well in these dense amorphous materials, under shear, for example, and this has been well established in steady shear, that the flow takes place via rapid sort of local rearrangements, which are plastic in the sense that they're typically irreversible when you go backwards, and these then cause strain fields around these. This is a snapshot of a displacement field around one of these, in time, around one of these plastic events, okay? And you can actually resolve, there's been some nice papers exactly how the system transitions through these various plastic elements through its states in sort of configuration space. So this is something that you can also see experimentally, but also, of course, in simulations. So based on that, you can build a sort of simpler kind of model, which are coarse-grained, and they're called elastoplastic models. Okay. In their simplest form, they are athermal, which is the regime anyway that we're looking at. So we have we ignore thermal fluctuations, and it's a mesoscopic model in the sense that this is a nice sketch from a paper by Posey et al. You partition the system schematically into blocks, and you look at each block and try and characterize that not specifically by what the particle arrangement is, but just macroscopic variables like strain or stress. Okay? And so the key ingredient in these elastoplastic models is basically, of course, changes due to the mechanical driving plus these plastic rearrangements that I mentioned, okay? You could build these models as spatial models, then you put them mostly on a grid. We're going to make this even simpler and generalize and do a sort of mean field version of this where we just throw away the spatial information and just look at the statistics of these blocks of the material. Okay? So it's called a mean field elastoplastic model. Okay. And there's been a number of studies of this model type already for systems under oscillatory strain. These are two papers where the lattice-based elastoplastic models were used, and they can, to a certain extent, replicate the experiments, but they're very hard to deal with analytically. You still have to run them numerically on a computer. These are the two mean field type models. This first one ignores the stress propagation, so it does have similar effects to what we've seen, but it doesn't have a genuine dynamical transition because every state's always, the system always goes to a frozen state, an elastic state. This system has a sort of phenomenological version of the stress propagation in it, but doesn't actually represent oscillatory strain. It's a sort of simplified model that in some sense coarse grains from one period to the next. So we want to do something that is more in that vein of a sort of mean field elastoplastic model, but that explicitly also has the stress propagation in it that results when something yields locally because that perturbs stresses elsewhere in the material. Okay, and these, do you see these kind of pings here? They're meant to indicate that if something plastic happens here, or rather this is drawn the other way around, if you look at this block, you have plastic events happening here, then that will affect what's happening in this other block. So it's sort of one of the earliest models of that type for in-mean field for athermal elastoplastic descriptions is the so-called Hébreux-Lequeux model. This looks at this coarse-grained strain field that I've just described. Let's call this local strains L in each of these blocks, which I've labeled by I. Okay, and then as its mean field, rather than looking at these individual LIs, it looks at the distribution of these strains across the system. Okay, and so it tries to represent what I've described, these local plastic rearrangements plus propagation of these perturbations. When something yields locally, it perturbs the stresses and strains elsewhere in the material. So the Hébreux-Lequeux model looks like this. So here you have a master equation, so time evolution of a probability distribution. You have a strain, which just says as you change the macroscopic strain by a rate gamma dot, you increment or decrement all the local strains. Here is the yielding term. This says once your local strain is big enough to exceed a certain strain energy E, so the energy here is worked out as a half L squared, so once a half L squared is bigger than E, that's what this theta function says, then you yield, so you have a plastic event with a certain time scale. That's given by tau here, okay? And the assumption is that after you've yielded, you have now a new local strain which is 0 because you've reached a new local equilibrium configuration, okay? And there's a balancing factor here which is the so-called yield rate, which just adds up how many elements are yielding and how many are therefore being recreated at a new strain, that's L equals 0, okay? And then finally, the important term that represents the stress propagation in the Hébreux-Lequeux model is just parameterized by this term here. So this says every time something yields, all the other elements receive a small perturbation to their strain, So this is modeled as a diffusive term in strain. And the idea is that as this effect comes from local yield events, the diffusion constant is proportional to the yield rate. So it's alpha times y, and this alpha is a so-called coupling parameter that represents things like, for example, the density of these plastically rearranging zones within the material. Okay? And this model is interesting because actually, depending on this alpha, if alpha is low enough so that you're in what's called a solid regime, you actually get a Herschel-Bulkley flow curve, in this case with a flow exponent of n equals 1/2, so it already represents some of the qualitative physics. There's an elastic modulus in this system in principle which I've set to 1, so I'll equate my strains with my stresses just to make the units a little bit simpler. So this model is very successful. What it's missing is it doesn't have any structural disorder. So it assumes every region of the material has the same yield energy, and we know that that's not true for these systems. There's certainly variations in local yield properties. So you can make a so-called disordered version of this, which is very similar, except that you now have a sort of distribution of possible yield strains or possible yield energies, which we call a rho of E. Okay, and we assume, based on simulations, that that has a Gaussian form for what we're going to do in the following. Okay, and now you have a distribution over the statistics of these local elements which involve strain and yield energy. So you have a joint distribution in E and L. You have largely the same terms as before. Okay, so again you have convection here. So convection in the sense that local strains move with the strain rate. You have the perturbing effects of the yield events on the other elements. And the thing that's really new is just this term here, which says that when you yield, you get reset to strain L equals 0, and you get a new yield energy which is drawn from this distribution. Okay, so that's the only modification essentially compared to the previous slide. Okay? So we're going to work with this model because the disorder is clearly important in these experiments that we've seen and the simulations where you have some regions that yield quickly and other ones that yield less quickly. Okay? We will look at slow strain, so we'll assume that the angular frequency times the characteristic time tau, that should be a tau 0, is much less than 1. And we will vary the strain amplitude, okay? And you'll see these rescaled control parameters with tildes. They're just scaled by the obvious powers of the average yield energy here. Okay. So what do we get out of this kind of theory? So the one thing that we can do more analytically is we can prove that this model really has a dynamical transition of the type you see in the simulations. So there really is a distinction between how the system responds at high amplitudes up here and low amplitudes. At high amplitudes you get these yielded steady states. At low amplitudes you only get what we call frozen states, so states which just move elastically. Okay? So the way you can sort of understand this is you could say, well, if I look at the yield rate and I average it over one period of my oscillation, which I'll call capital T, then up here that's going to be non-zero because I keep dissipating energy, I keep having yield events. Okay? And then as I lower the amplitude, what can happen is that at some point this yield rate goes to 0, and that's this dynamical transition that I've mentioned. Okay? So that's when the system basically freezes. Below that point, the only steady states that exist are frozen steady states where the system only responds elastically. Okay? And so the question then is, how do we actually work out where this transition lies? Okay? So I'm going to just try and explain a little bit how this argument works. So this is the only slide with maybe the more complicated looking equations on it. But just to get the idea across here, so what happens in this system as you approach this dynamical transition, of course the yield events get very rare. So the yielding dynamics is slow, so the average yield rate is small. And so this so-called strain diffusion, so the perturbing effects that happen on a local element are rare. Okay? They're rare and slow. Okay? So what we can then do is we can basically take a limit of that description towards that transition by looking at a normalized rate, okay, for these transitions to occur. And it turns out, and really the most important thing for me is to try and get across to you these things in red rather than the math necessarily. Okay. It turns out there are two types of yields that happen near this dynamical transition. One are the indirect yields, okay, where you have a local element that over many cycles is basically just being moved back and forth. But occasionally something somewhere else in the material yields, and then this local strain gets a little perturbation, and then manages to cross its yield barrier. So that's what we call an indirect yield, because it's not directly caused by the perturbation, but it's caused by stress perturbations coming from elsewhere in the materials. Okay? And the way we are parameterizing our strain, this happens only at the extremes of the deformation of the material, right? Which makes sense, because that's where you have the highest chance of yielding if you're only getting small strain perturbations, right? There's a second class of yields, which we call direct yields, which is when you've just had a yield, but you've had the sort of misfortune of landing in a state where, for example, you have a low yield energy, and the next time an oscillation happens, you yield again immediately, right? So that can also happen. So these are these direct yields which happen in the next period, right? And so it turns out what we could do is we can write a closed set of equations that link the rate at which these types of yield events occur, and then we can convert that into statistics of the steady state distribution over strains and energies, and eventually back out where this transition will occur. Okay? So that's something that we have to do numerically, but essentially that's a relatively simple operation. One can also simplify the theory and only account for these indirect yields. That gives us slightly lower estimate for this amplitude. What's interesting also is the comparison with the original model, which only had a single yield energy. There, this dynamical transition is actually very simple, and it's a straight line, because it just tells you if your amplitude is lower than your yield energy, then you never yield. If it's higher, then you always yield. Okay, that's why in this case it's a straight line. Okay, and so it turns out that the fact that we have structural disorder always makes the system more likely to end up in a frozen state and less likely to end up in a yielded or fluidized state. Okay, so that was the first part of the phenomenology that I told you about at the beginning. It was this fact that there is a dynamical transition in the steady state of these systems. Okay? But what we haven't looked at is this interaction between the two kinds of non-equilibrium, namely the interaction of the strain amplitude and the initial preparation of the system. And so for the theoretical analysis, what we're going to assume is that the initial annealing is represented by a sort of Boltzmann-like annealing factor on our yield energy distribution. Okay? There's no minus here because I'm counting the yield energies downwards in some sense from a reference energy, so therefore there's a plus sign here. Okay? So this parameter beta will tell me how well annealed the sample is. Beta equals 0 is something that's basically just been stirred, right, and has the sort of prior distribution of yield energies. Beta, the largest value that we look at, is 70, something that's very well annealed. Most local regions have very high yield strains in that system. Okay. Okay. So let's focus first on the poorly annealed samples. Okay, so what I'm showing you on the right here is basically the analog of this simulation plot on the left. We can do the same thing with our mean field model. We basically run the dynamics through a number of cycles of shear until we reach steady state. Then we record, in this case, the energy as a function of the strain in this steady state that we've reached. And you see for these poorly annealed samples, which are these top curves here, this looks very similar to what we have in the simulations. There is a characteristic strain where all of these curves meet and they all have the same energy there. Okay? So that's sort of the limiting frozen state in some sense. Okay? So all of these samples are still frozen in the sense that they behave elastically in steady state, and then beyond that point we have the fluidized states, okay, which are where the energy is a unique function of the strain. Okay, so you see this is a very good sort of qualitative match between the theory and what happens in the simulations. Even though the theory is relatively simple, it's only a mean field model that ignores a lot of spatial structure. Okay, so that was the poorly annealed samples. Let's look at the better annealed samples, and here you see one of those. So this is one where you start in a low energy, so that's a higher beta. And you see again, as in the simulations, in this case the yielding happens later. So you have to increase your amplitude and go through a sequence of steady states, and you get to a large amplitude before the system actually starts fluidizing. So again, that represents what happens, that matches what happens in the sort of detailed particle-based simulations that people have done. More interesting still is the dynamics. Okay? So far I've only showed you the information about steady states. Okay? So now we're going to make this a bit more, have a closer look and actually look at what happens as we really strain the samples over multiple strain cycles. Okay? So here's the energy as a function of strain cycle in a well annealed sample. Okay? And you see, depending on strain amplitude, here's a large strain amplitude. Here the energy goes up more or less from the word go. You reach a fluidized state. As you lower the strain amplitude and you repeat the experiment, the energy stays essentially constant for a long time, and then very late, sort of in the day, it starts to increase and reaches this fluidized state. And at a lower amplitude still, basically the energy just goes down, and then we cannot record it any further because the system is basically frozen, but then it settles to a constant because that's the frozen state. Okay? So the energy already shows you that something interesting is happening. More interesting is if you look at this from the point of view of the yield rate. So you ask how many events are happening in each strain cycle, essentially. That's the period average quantity from before. Right? So that's why it has these slight wiggles here at the beginning. So you see that up at high strain amplitudes, much what you'd expect happens. The yield rate actually goes up from the beginning, reaches a fluidized state. But then what's interesting is this regime in between here, where the yield rate first goes down, and then eventually you very rapidly reach this fluidized state, right? So you have something where dynamically you have some kind of reentrance where the system always almost reaches an elastic state, and then at the last minute it sort of turns around and refluidizes, right? And that's kind of interesting because that's not necessarily what you'd expect, right? You might expect that the system either directly goes to a fluidized state or it directly goes to a frozen state, right? So here what happens is it more or less misses the sort of frozen state by a little bit, and then eventually still goes to a fluidized state. Right? We can quantify that by asking, well, how many cycles does it take before the system actually fluidizes? We can measure that in various ways. Let's focus on, maybe for now, these blue squares here. We just measured that, defined that by saying, when do we reach 75% of the final fluidized yield rate? Okay? So that's basically somewhere near here. So that's, we say, okay, at this point the sample has reached fluidity, it's been fluidized. Okay? And so what I'm plotting here is how this quantity varies with strain amplitude. Okay? You see at high strain amplitudes, this thing is basically 1, so you fluidize almost immediately, and then as you decrease the strain amplitude, you see something that, to a reasonable approximation for a while, looks essentially exponential. And that's actually something that people have sort of used to fit experimental data also in these systems, that as you lower the amplitude, the amount of strain cycles you need until the material yields basically goes up quite strongly in a roughly exponential fashion. Okay? So that applies in this range. Then of course, as you reach our dynamical transition, right, the transition where the actual steady state changes, right, this time has to diverge, and it turns out if you then look at how that divergence happens, it's basically a power law, and we find it's consistent with something that's roughly a square root divergence. Okay. So these interesting phenomena happens here in this transient behavior. Okay, so we have this near freezing, and then we have this refluidization in the system. And there's a name for this actually, which in material science is basically called, this is fatigue failure, right? So you tire the material out by straining it so much that eventually it's going to fail, right? This has been looked at, for example, also in experiments on metallic glasses. Here's a particularly drastic macroscopic example. So this kind of delayed yielding, as we saw it from the plots, right, we would identify as basically the analog of what the material scientists call fatigue failure, right? But interestingly, it's not a mechanism that relies on accumulation of damage in some sense, right? It's actually a different type of dynamical transition, and that's sort of an interesting question. There have been papers from other groups that have sort of propagated more this kind of accumulation of damage picture. That's not what comes out of this kind of description. So let's look a little bit more at the mechanism there of fatigue failure. Right? I've plotted for you here the yield rate as a function of number of strain cycle, and broken down into the contributions from the different yield energies. Okay, so that's why this is a three-dimensional plot. Okay, so what you see is that in the first cycles, which is over here, some very small n, all of the yielding basically happens in the elements that have got low yield strains. And that makes sense, because those are the things you break them immediately, you make them yield, right? And they become more stable after that, at least statistically speaking, right? And then eventually this yield rate sort of goes down, and then gradually also some of the kind of elements with high yield energy start to yield, right? So this plastic activity at the beginning is dominated by this direct yielding of these rare elements, which are shallow in the sense that they are low-lying, they are sort of fairly high-lying in the energy landscape, they have low yield energies, okay? And then what happens is that this yield rate keeps going down, as I showed you on the previous plots. The system always reaches a frozen steady state, but then it refluidizes. Okay? So that's the origin of the slowing down in this case. Right? So you have a sort of dynamical transition where you more or less miss a fixed point, and then you reach another fixed point, which is the fluid one. Right? And there's an interesting question also theoretically here, because this system, as I'll try and explain now, essentially has infinitely many absorbing states. So if you think of this from a sort of broader perspective of non-equilibrium statistical physics, you might have heard of absorbing state phase transitions. The key example is directed percolation, right? Where basically once you've reached a state where everyone's died out, then you've had your sort of phase transition, right? So these are called absorbing state phase transitions. So if we look at our system schematically, and we just plot it on sort of two axes, which is the probability of states with high yield energies, which I'm calling stable, being occupied, and states with low energies, which I'm calling unstable here, being occupied, right? Then basically you have an infinity of absorbing states, which is basically you just need states to be occupied which are stable at your given strain amplitude, right? Because as long as all of the regions of the material are stable under that particular strain amplitude, then nothing else is going to happen, right? Then you've reached your steady state. But there are many such states, right? Because all you have to make sure is that the whole distribution is just on those stable elements, right? Which in this picture means I'm on this axis here, I've got no probability for unstable elements. All regions of the material are in this sort of stable state, right? So this is a system that has not just one absorbing state, but infinitely many, right? And schematically, that's something that we're working on at the moment, the sort of flow in time as the system proceeds with its evolution, right, can either, from its initial condition, hit one of these frozen states, and then you're done, that's your steady state, right? Or it can reach the fluidized state and sort of miss this frozen manifold, if you want, this manifold of absorbing states, and then it goes to a fluidized fixed point, which I've not tried to draw on here, okay? And then this, the situations that we see where the yield rate goes down almost to zero to then kind of re-increase again, basically look almost like this blue trajectory, so where you just get to the limit of this set of frozen states, but then you depart again and go towards the fluidized state. Okay? So that's how this sort of fatigue failure phenomenon happens in our model, right? That you have this infinity of frozen states, and if you have an initial condition that's near a trajectory which just misses those, then you can basically almost get to one of these limiting states, but then you miss it and you refluidize. And there is an amusing analogy, and I'm really not sure whether this is any more than a sort of pictorial analogy or whether it's actually helpful. But I've asked around, there's not that many models that actually have an infinity of absorbing states, right? Mostly there's things like DP that have a single absorbing state, directed percolation, okay? But there is an RG, a renormalization group flow, for the Kosterlitz-Thouless transition, which has a very similar looking structure. So now the flow is in RG, so it's increasing length scale of your physics, and on the two axes you've got temperature and basically defect density. Roughly, I mean, these are actually scaled variables, but that's sort of physically roughly what's happening there, right? And this flow also has a whole line here of fixed points, and if you start with a low enough defect density, then at macroscopic scales, you'll go to this zero defect density, one of these zero defect density fixed points, whereas if you start with a high enough defect density, then you get to a state with a macroscopic finite density of defects, okay? And so this has a very similar structure. The actual limiting curves here look different, and that's because in the Kosterlitz-Thouless RG flow, it turns out both flow directions are sort of quadratic in the perturbation in some sense, and that's what makes these lines here have a sort of finite angle, whereas in our case, from the equations, we think the structure looks more like this, that it's actually parabolic. So I think that's the sort of broader questions from the sort of statistical physics of non-equilibrium systems is this kind of a similar universality class to this one? Are there other systems that look like this, right? Etc. So there's all sorts of interesting questions that we want to pursue also there. And one obvious one is to see whether one can work with a simplified representation like this and understand some of the sort of physics that we see, at least within our model. There is also a further connection, which I'll mention how am I doing for time? I've got 5 minutes, that's plenty. I won't need that much. There's another amusing connection, which is the connection to creep. Okay, so creep is doing what I talked about right at the beginning. It's just applying a stress and then holding it. And then you watch what the material does. And typically, if you keep the stress constant, it will keep moving. And then the question is it going to move and start flowing, or is it just going to move a little bit and then essentially stop? Right? And if it does the second thing, then you call that creep. So if it moves very slowly, okay? And so you can ask a similar question to sort of what we were asking with our oscillatory strain, right? So you can apply this constant strain, which is here called sigma, and then over time you can watch the strain rate. So you can watch how much is the system actually deforming, okay? And you have a sort of graphs that actually look temptingly similar to what we had in our system, except we were plotting yield rate, okay, because our strain rate's fixed externally. So it's not exactly the same physics, okay? But here also you have this phenomenon that under creep, the system can basically almost stop moving. The yield rate gets to a very low value, and then eventually you reach a steady state, okay? So there's another interesting question here of whether there's a useful analogy that can be drawn. There's a nice paper from Mathieu Viard's group where they tried to build a sort of scaling theory of how these curves look. And they get out various scaling exponents for how these curves should look, both at the sort of critical value of the stress, but then also either side of it. Okay. So if you compare that with our curve, as I say, there's another interesting question there, whether that's a useful analogy, whether we can actually maybe take some of the ideas from this paper and build them into a sort of Landau-like description of what is fatigue failure, right? Or maybe the analogy on the previous slide is more useful. You see that's kind of an unsolved question at the moment, and we're trying to work out what the sort of best simplified theory is that really tells us about this fatigue failure phenomenon. Okay, so let me summarize there. So what we've done within the model I've shown you is we've analytically characterized this dynamical yielding transition. That's something that we can now show that this model that we're using, this disordered Eborle-Kerr model, really has a dynamical transition under oscillatory strain. And at high strains, you have these yielded steady states. At low strains, you only have frozen states. Okay. We get from this model not just the steady state phase diagram, but also the history dependence, the interaction of the two kinds of non-equilibrium. Looks very much like what people see in experiments and in MD simulations. And then we find in the dynamics that there is this interesting characteristic behavior that looks like fatigue failure, where the material looks like it's going to more or less survive in an elastic state until it sort of yields at the last minute. Of course, there's various things that we would like to do that I've already mentioned. So we would like to build a sort of scaling theory of fatigue failure, maybe using these schematic ideas that I mentioned before. There's also the general question of how does this relate to other systems with infinitely many absorbing states. More specifically for kind of this strain of amorphous materials, we would also like to improve these models, because what we actually know is that the Eborle-Kerr model is not a terribly good approximation for stress propagation, because the way stress propagates from a plastic event is actually in a power law fashion. So you get some very large stress perturbations, some very small ones, and actually the mechanical noise is not Gaussian as supposed in the Eborle-Kerr model, but it has a power law distribution. So there's interesting connections there also to Levy walks and Levy dynamics. And then there's just a further question, which is what happens if you now start including thermal activation over barrier? So far everything we've done is athermal, so what happens to the phenomena I've described once you start adding small amounts of temperature is also an interesting question. And we've recently had some funding, so if anyone has any good candidates for PhD positions in this sort of modeling, but more applied to sort of active matter, in particular the cytoskeleton, or if you're a potential candidate yourself, then by all means, then come and talk to me. Thank you very much.
Thanks, Peter. Questions?
Hi. Right. So I have two questions. So the first one is, when you look at, if you were to probe the transients between the marginal state where you have the star and you further go out for the well-annealed glasses. Mm-hmm. If you were to look at the transients in way the system approaches the steady state, are there differences in the way it does it in this window of strain amplitudes?
Let me see. I think if I've understood the question.
No, so you had it in the last one slide. The previous one. Yeah. So you have a star, which is the poorly annealed glass.
Right.
And then for the well annealed glass, you are able to shift this transition to higher strain amplitudes.
Right.
So I was wondering if in the window between the star and the actual liftoff for the well-aligned glasses, if you were to look at transients, do you see something anomalous in the way the system behaves as it approaches the steady state?
Absolutely, and this is basically that strain window. So if I go back to the...
that is that strain, okay.
If you go back to this slide, all right. So this is actually the range between... Sorry, this is, let me go back to the strain scale so we can see this properly. So you see this is kind of 1.2 times gamma star, right? So for this system, I'm looking at transients sort of in this region, okay? In this region, there's actually not much that happens that's very different from what happens on the, further on the left, in the sense that those systems all look like this. So the yield rate just dies and the system freezes.
Right. Thanks.
I mean, what you do see, I mean, in that sense, your question is interesting. Of course, if you're very close to this point where so not near the star, but on the other side, so if you're basically where the circle is, but just to the left, right, then of course you see the remnants of this kind of, in some sense, critical transition, and so you see that the relaxation there is a power law, whereas if you go to lower strains, then it's faster. Okay. So yeah, you do see a signature in the sense that as you approach to transitions, as you go beyond gamma star, right, the way the system reaches its steady state becomes slower and slower, eventually becomes a power law.
So from an experimental perspective, what would I look for in an experiment to see this, meaning what would be the rheological signature that I can measure?
So the yield rate should be linked to dissipation, right? So in principle, you can measure dissipation per cycle.
Yeah.
Okay? We have not actually checked within the model, but that should be a reasonable proxy, I think.
Number of events? Can you measure number of events?
Number of events, yes. Yeah.
Yeah, if you can measure the number of events, even better, right? Because that's directly this, right? But of course, that requires more analysis. If you only have macroscopic stress and strain, then the dissipation should give you a reasonable proxy, I think. Yeah.
Hi, Peter. So there are all these complex memories that are lying just below this yield threshold.
Yeah.
I mean, so have you thought about how one can get from these kind of simple models, or what needs to go into the models to get you all this?
What memory phenomena are you thinking about specifically?
So, I mean, so for example, you can get this very interesting limit cycles and with a lot of structure in these limit cycles and so on. So
yeah, so obviously within this type of model, we cannot get the things that Mohitian has looked at, for example, right? Exactly. So this is sort of beyond our level of resolution because this is configuration space, right? All our elements in some sense are interchangeable, right? So that's a good question. I think I don't have a straightforward answer to that. So the things that we can see are basically everything that's to do with local strain, the hysteresis in the sort of across the sort of strain loops, the dissipation, right? But obviously we cannot see anything that's related to the spatial structure. So that's basically if we had to sort of take Mohitian's diagram and sort of scramble everything, right? So that's our level of resolution. But we should talk about that. I think that's an interesting question. Yeah.
So recently we looked at instead of shearing in one direction, multiple directions with one of my colleague in Hyderabad. And we do see that you can actually relax the system much better if you do it multiple directions here.
Okay.
But this phase diagram remains more or less similar. And we also found interesting limit cycle. Like if you try to shear twice in XY, once in YZ, and then ZX, then you have a limit cycle which is 1, 2. So you have 3 limit cycle, 2 limit cycle, all sorts of things. And if you randomize this protocol, then you never reach a limit cycle. So it evolves ever and ever, and at least in our simulation we could not reach the steady state yet.
I see.
And that's why I was asking whether some of these features can be captured, or even if we try to capture it, let's say in a mean field model, what will be the ingredient which should go into?
You could certainly make this model tensorial, right? So you can basically have a strain tensor, right? And you have a distribution of yield energies that carries over. I think that would carry over more or less as it is, and then one could look at protocols of the type that you mentioned. So I think that can be done. We haven't done it, but I think that's also an interesting avenue, definitely.
So one more question, and so can you go back to this experimental data of so this one, let's say here. So you said that when you go below this poorly annealed glass or to the well annealed glass regime, then your yield strain systematically moves.
Yeah,
and that you do capture in the elastoplastic model that you are looking at.
Yeah.
So in the elastoplastic model, what is it that controls the shift in strain?
Broadly speaking, it's the way we prepare that we assume the sample is prepared, right? Very roughly, right? You could think of sort of the system as being stable up to strains where basically you've eliminated a minority of the initial preparation of the system. So you eliminate all the local regions with small yield energies, right? So if you've already started with a system that has very high yield energies, then obviously you could strain to a much larger strain until the system really starts showing noticeable plastic activity. And that's essentially the trend, right? So I think essentially that strain in our system, although I haven't checked, because we haven't got that many data points, it would scale more or less like the mean or the root of the mean of this initial yield energy. Okay. So it's basically just how stable is the system, how far can you strain most regions of the system without them moving. Right, that's essentially what's happening.
Yeah. So it's basically the typical barrier that you need to cross if you want to have a...
Exactly, and if you start with a system that's so well annealed that all the barriers are high, then of course you can strain to a larger strain. So I think that's entirely consistent with intuition.
Yeah.
Following up with Rajesh's question, so you have this plot for these poorly annealed and well annealed glasses where you show in terms of energy of the system, right? So in experiment it is really difficult to measure. So I was wondering that you mentioned about the dissipation. So one way to look at it is area under these Lissajous plots or something. So how? So is there a correlation between the energy of the system and the dissipated energy? Do you get similar kind of response, like if you calculate this hysteresis of stress strain?
So as I was saying in response to the question earlier, I think if you look at dissipated energy per cycle, it would look roughly like this. Okay. So you'd get a signal that should look similar to the yield rate, right? On the basis that essentially there's a sort of order one factor between yield rate and overall dissipation, right? I mean, the amount of dissipation is not directly proportional to the number of events, but there's a factor in there that doesn't vary a huge amount. It depends on the yield barrier, etc. Right? So I think if you're doing what you said and measure these kind of dissipation per cycle, you would get something that looks like this, right? The energy actually, if within our numerical resolution, it actually looks like the energy qualitatively also looks like this, in the sense that it first goes down a little bit and then it goes up. But of course the effect is much more drastic in the yield rate, because the yield rate goes essentially to zero. Okay. Right? And actually within our numerical, actually we're not really completely sure whether this is a numerical artifact and it's more or less flat or it really goes down. In the MD simulations, you see that there is a slight decrease of the energy, right? So you still have a little bit of strain annealing, okay? But I think the dissipation or the number of plastic events would definitely be the better quantity, because you have a much bigger signal and a much bigger qualitative change. Yeah.
Okay, thanks.
Okay, last question.
Yeah, I have a question following the comments by Pinaki about memory. So you said you don't have configuration space, but you have energy loops, right? And I think the strategy to have memories is basically to do cycles and vary the amplitude of the cycles. Mm-hmm. So you think you could do that in your model just by having a first loop in energy engine, just having a reduced amplitude of cycles, and therefore be able to embed this type of
yeah. Mm-hmm. That's a good point. Yeah, we could certainly play with protocols where you change the amplitude. Yeah,
exactly.
We haven't done that yet, but that's a good point. Yeah.
Okay, you think it'll be possible in principle?
Yeah, sure. I mean, in principle, we can run any sort of strain history with this type of model. We just have to solve it numerically, but that's not an issue. So.
Okay.
Yeah.
Then I have another comment about the comparison between your transition and that of Costa-Tholis. So another type of absorbing transition with many absorbing state is the mana-Senbine model. So I wonder whether you consider that, because I'm not sure if it's exactly the same type of flow curve that you would have, but that's certainly another type of this many absorbing state transition.
Okay, interesting. Yeah, we should talk about that. I mean, I'm not sure whether in the mana model it's sort of the orders, the different absorbing states are sort of macroscopically different, right? That's what we have here. So there are macroscopic order parameters in principle that distinguish those, but we should talk about that. I think that's an interesting idea, yeah.
Okay, thank you.
Okay, let's thank Peter again for a nice talk.